Okay, let's take a look at some workbook problems now. Um, Again, we're trying to go really heavy on synthesis and reactions. And we're going to think about that. I think maybe it's a more reasonable way to learn things instead of trying to tangle everything together. Um, you don't necessarily have to know mechanisms to do the synthesis problems. It's just, I like to think about things that way, but I think for a lot of students, they just end up memorizing a lot of stuff anyway, so. And even for students that don't like to memorize, like, that's not really how I learn the subject, although obviously I memorize some stuff. You don't really want to be thinking about mechanisms while you're doing synthesis, at least not in any kind of great detail. So just because you know the mechanism for reaction, you need to be able to like recall the reaction and the products and the radioselectivity and all these different types of things really rapidly if you're going to solve these problems on any kind of reasonable timeline. Okay, so let's look at these problems. This is the first problem from 7.10 on page 76. So this is page 76 of the workbook. We're just looking at the very first problem they give us. So this is more typical of how synthesis problems are given. You're given some material to start with, and you're asked to transform it into some sort of product. And you'll see there's a question mark here saying, well, how do I get between those starting materials and that product? So this would be similar to, in our chocolate chip cookie analogy, if you're given a bunch of different things like flour and eggs and all this different types of stuff, and asked how to make chocolate chip cookies, this is asking you to kind of give the set of instructions that would allow me to go from these starting materials to this product. And so there's myriad different ways to kind of work at these problems, and you kind of have to figure out what works best. But I'm going to show you the way that I think about these, which I think is a good way to think about them. So the first thing you want to do, you want to kind of try and break this down to smaller problems. The tough thing, the very difficult thing in organic chemistry, is the carbon-carbon bond forming reactions, and you're going to learn a lot of those in the second course. So you need to get pretty good at dissecting those now, I think, if you want to survive the second course. The second course is pretty hard. But yeah, let's take a look at this molecule. So we're starting out with this. We're going to label these 1, 2, 3. And I notice when I come over to here, this molecule it's not 3 carbons, right? It's 6 carbons. So what this tells me is that I must have formed a carbon-carbon bond forming reaction. I'm sorry, I must have formed a carbon-carbon bond. And that the most likely thing that happened here, right, is that I took 2 of these molecules and stuck them together. If I start out with three carbon units and I end up with 6, it makes sense that I would, just take 2 and sort of stick them together. And we can't do that directly, but we can use some chemistry to do that. So the way these problems are typically posed are, one, we give you the starting material. We tell you can't use carbon atoms that aren't given to you as part of the starting material. So you can't just invent molecules that have carbon atoms in them. If the carbon atoms aren't in the starting material, or if the carbon atom is in the product, all of them have to come from the starting material, right? So I can't invent carbon reagents. I couldn't say, well, how do I make this? I go to the store and just buy this as my starting material. I can't just say, well, I'm just going to go buy that, and that's my reagent that I'm using, and thus I'm done with this problem. Obviously, you haven't really done anything. So somehow we have to take the carbons that are in this and transform them into that. All right, so how are we going to do that? What I like to do is to use retrosynthesis to look at where the carbon-carbon bond break happened. And then I think in the forward direction once I get past the carbon-carbon bond forming part. So you can kind of broadly think about things. You have your carbon-carbon bond forming piece, okay? Or let's say not reaction, but kind of like series. And that's where we're starting at. And the second part we're going to look at is going to be just like these simple, like I would just call them functional group transformations. And this is kind of what you have memorized at this point, functional group transformations, things like alkene to halide, or, like in the last video, we looked at alkyl halide to alkene, or dihalide to alkyne. Those are functional group transformations. And that tells you how to go from one thing to another with just reagents. And then carbon-carbon bond forming series, that's just the series of reactions that you need to form the carbon-carbon bond. And for us, at this point, that's just the alkylation of the acetyl-iodine ion. It's deprotonating alkyne and alkylating it with alkyl halide. Okay, so I'm trying to think backwards here, right? So let me draw this down here, because I know you guys are just now kind of dipping your toe into this deep ocean of organic chemistry stuff. So the carbon-carbon bond forming series, we know that we're going to use this reaction. Okay. From this, I just said don't worry about the mechanisms, and I'm drawing one out. For these, I think it's a little bit easier, but just because it tells me, it makes it easier for me to see where the carbons connect in, but it's sort of up to you how you want to deal with that. I'm going to put a prime on that. Okay, so this is our carbon-carbon bond forming reaction. And let's put some colors on that. So I've got this here, and I'm forming the bond there. So when I snap these things together, that contributes its carbon to the bond, and the other side contributes its carbon. So it's this magenta carbon and this kind of violet carbon that come together to form the new bond. Okay. Okay. So we know that if we're going to form a carbon-carbon bond, and we're going to use this little strategy here, that at some point we can infer that this must have had an alkyne in it. Okay, so we're trying to go backwards. We're just saying, just like we would for a chocolate chip cookie, that we know that a chocolate chip cookie at some point was just raw dough. I'm saying, well, this alkane, if we formed a carbon-carbon bond reaction, must have started out with an alkyne in it. So I'm going to go ahead and I'm going to number this. And you'll see now that I've numbered it that I've actually messed up and lost a carbon, which just emphasizes the importance of numbering your carbon so that you don't lose anything. If it can happen to me, it can happen to you. All right, so let's take a look here. So we know that our starting material has 3 carbons in it. And we can see that this thing is just kind of connected linearly here. And so the reasonable thing to think about here is that carbon 3 and 4 must have been brought together somehow. So I think I'm, maybe I'm getting a little bit ahead in thinking all the way back, but I think you kind of need to. What I'm saying is that, like, this bond here must derive from, I'll even get rid of that, so it look a little more similar. Okay, I'm saying that this started out as 2 of these little subunits that I started with. So I can use 2 of these, like I got an infinite number of starting material molecules to work with, and I just kind of somehow took this, and I needed to click it together like that. Now you know that there's no reaction that we know to just join those 2 things together. We can't just take 2 alkynes and heat them up and then hope that they form this 6-membered chain. Okay, so that's where we want to connect it at. So now we have to kind of work backwards to understand the chemistry that we had to use to do that. And so there's a lot of, there's a couple of different ways I can imagine doing that, but I'm going to try and do what I think is the most easy to understand. So if carbon 3, let's say, is indeed this magenta part, and I come back to this prototypical, or this sort of canonical example up here at the top, what I'm saying is that, well, that means that carbon 3 at some point must have been an alkyne, must have been an sp hybridized carbon, must have been part of an alkyne. So I am just going to say, okay, so that's carbon 3, it's now an alkyne, and I'm not going to mess with carbon 4, we're just going to leave it alone for now. Now we do know that carbon 4 and carbon 3 had to come together at some point. Okay. All right, so now that I've gotten here and I figured out where the alkyne went, the problem gets a little bit easier because I know that I just need to split it right there. Right, so in this reaction, I'm looking at it in the forward direction. Thinking about it, I can see it in the forward direction, that's how I have it written, but I want to be kind of imagining it in the backwards way. And so I'm just doing the same thing here. I'm saying, okay, well, I'm going to think backwards now using that reaction. I'm going to say, well, if I split that, what did it look like before? And, for me, I'm going to get this right on the first try because I've done this a whole bunch of times. For you, it might take a couple of tries to kind of be able to do these problems. So don't get discouraged if it takes a little bit of time. But yeah, let's take a look at that. So when I break that bond, I know that half of it, the magenta portion over here, becomes an anion. And we've drawn that out properly there. But what happens to the other half? That must become this halide thing. Right? So carbon 4 now we're going to have to put a halide on. And that's what we've done here. So I've just taken, ooh, did I pick up an extra carbon there? I sure did. Okay. So now we're going to have to take that, and that's that carbon atom. Okay? All right. So this procedure that I've done, so this, you don't have to do this part if you don't want to, but this procedure that I've done takes me back to the point where I don't need to think about carbon-carbon bond forming reactions anymore. Now I have two sort of fragments, two carbon fragments, I guess you could say. These are two fragments. And now I want to take those fragments and I can kind of split those up into two separate synthesis problems. So now I can ask myself, I'm starting with this. I'm going to pick one to start with. It doesn't really matter. Let's say, how would we make the alkyne? So if you watch the last video, you'll remember I said we have a recipe for that. Okay? So I want to make this alkyne anion, ultimately. So now it's like we've taken this big synthesis problem, we've broken it down into much simpler synthesis problems. This part to me, outline here. This part to me, this top part that I've done, which is this, the carbon-carbon bond forming series, that's really the hard part. If you can get through that, you're mostly done at that point if you know your reactions. But you'll see it's not trivial to do this. It takes some practice. Yeah, so how do I go between these two things? So let's see. So my first reaction I know, because it's literally the only reaction that I know. Right? For an alkene, if you look at your flashcards or if you have your reactions organized, the only thing you know how to do with an alkene is take this, add in some light and some bromine, and I get this out of it. Okay? Now there's no